Welcome to MEI Numerical Methods, Numerical Integration. In this video we'll be carrying on looking at the trapezium rule. Now in this table we have the values that we found in the previous example where we were approximating to the integral of 1 over x between 1 and 2, and we found there that the trapezium rule estimates converged on the exact value 0.69315 from above, whilst the midpoint rule estimates converged from below. And in the last two columns of the table here we've got the relative errors for the two methods, and obviously as the number of strips increases the relative error goes down, but notice that the error for the trapezium rule is significantly larger than for the midpoint rule, and in fact it can be shown that we would expect the relative error for the trapezium rule to be approximately twice that for the midpoint rule. Now we can show why it is that the trapezium rule approaches the true area from above and the midpoint rule approaches it from below for this particular shape of curve, because we've got in the left hand diagram we've got the larger trapezium is the one that's being used in the trapezium rule, so that's clearly the area underneath that is greater than the area underneath the curve, and we can show that the lower trapezium actually has the same area underneath it as the area that we calculate for the midpoint rule, because in the diagram on the right hand side we've got the rectangle that we use for the midpoint rule is got an upper edge indicated by the horizontal dotted line, and because these two triangles have the same area, if we start with a rectangle and remove area A and add area B instead, and they've both got the same area, so therefore the trapezium has the same area as the rectangle. So we can see that the area under the curve for this particular shape of curve is sandwiched between MN and TN, although it might be worth noting that the point of intersection between the curve and the upper edge of the lower trapezium isn't necessarily the tangent to the curve, so the proof that the area is between those two values in all cases might be a bit involved, but hopefully that's sufficiently plausible for the moment. Now, just to mention some of the terminology involved with these curves. The curve in the diagram would be described as being convex, but the area underneath it would be described as concave, rather confusingly. And the idea with a convex curve is that if you've got one definition is that a line connecting any 2 points on it consists of points entirely above the curve. Now that's not particularly memorable. The way I remember it, completely unmathematically, is when you come to cover the function y equals e to the x, that has that shape, so that would be a convex curve. Now, as far as the area underneath the curve is concerned, a convex area is defined by the fact that any 2 points in the area, i.e. under the curve, if you join them, then all the points on the line joining them are within that area. So that's perhaps a bit easier to remember. So then a concave area, which is the one we've got in our diagram, is where we're interested in the area under the curve, and it is possible to find points where if you connect them up, the points on the line don't lie in our area under the curve. So in the case of a concave area, we've just seen that we have that inequality, or those inequalities, and this does provide a handy interval in which we know the area is going to lie. So even if we haven't got very good estimates, we can say, as soon as we've got the midpoint estimate and the trapezium estimate, we can say that the area must lie between those two limits. And then when the curve's the other way round, where we've got a convex area below the curve, then we can see that the trapezium rule involves the lower trapezium, and the upper trapezium can be shown to have the same area as the rectangle in the midpoint rule. So again, our area is sandwiched between the two estimates, but it's the other way around this time. Now, there happens to be a useful relation between the trapezium and midpoint rules, as shown on the screen. And if we note the formulae for the trapezium and midpoint rules, and then consider what happens if we double the number of strips in the trapezium rule, so that we've got h over 2 is now the width of each strip, but we're going to continue with the notation of fn as being the value of the function at the right hand end of the interval, so that appears in the formula for t2n as well. But whereas for tn we had f1, f2, etc. being appearing as the intermediate terms, in addition to those for t2n, because we've got double the number of strips, we've also got some extra edges of trapezia. And then if we put brackets around all of this bit, you might like to study this later in detail, but we can see that all of those terms within the square brackets will fall into either the trapezium rule estimate or the midpoint rule estimate. So we get that relation. So that's everything on the trapezium rule for the moment, and we'll be looking at Simpson's rule in the next video.